On December 27, 2004, instruments around Earth caught one of the strangest signals ever seen. Some detectors saturated almost at once. Others were partly blinded. The source was not the sun. It was not a normal gamma ray burst from another galaxy either. It came from inside the Milky Way, from a magnetar called SGR 180620, roughly 30,000 light-years away. That distance is the first detail that makes the story feel unreal. If the source sat about 30,000 light-years away, then the flare we noticed in 2004 had actually happened about 30,000 years earlier. Long before cities, long before writing, long before the pyramids, this star had already erupted. Earth was only receiving the message after a journey that lasted longer than human civilization. So the title sounds like breaking news, but the truth is even stranger than clickbait. It was 1 minute ago for our instruments. It was 30,000 years ago for the star. Space does that all the time. It turns distance into delay. When you look up, you are never seeing the universe as it is right now. You are seeing old light arriving late. A magnetar is what remains after a massive star dies and its core collapses. Imagine a star heavier than the sun getting crushed so hard that most of its mass is packed into a sphere only about 12 miles across. That is a neutron star. A magnetar is an even more extreme version, wrapped in a magnetic field so violent it changes the behavior of matter itself. Scientists describe magnetars as some of the most magnetic objects known in the universe. Their fields are trillions of times stronger than Earth's magnetic field. That is not the kind of number your brain easily pictures, so use this instead. A simple fridge magnet is harmless in your hand. A magnetar's field, if it came too close, would begin tearing at atoms, electronics, and chemistry long before the star itself arrived. But magnetars are not always quietly sitting there like cosmic relics. They can twist, their crust can crack, their magnetic field can suddenly snap into a new shape. When that happens, they release huge blasts of X-rays and gamma rays. Astronomers call the rarest and strongest of these outbursts giant flares. They do not happen often. That is part of why the 2004 event became legendary almost immediately. SGR 180620 had already been known as a source of repeated high-energy outbursts. That is what the letters SGR mean, soft gamma repeater. But on that December day, it did something far beyond its usual behavior. For a fraction of a second, it became so bright in gamma rays that it overwhelmed instruments built to watch some of the most violent events in the cosmos. This is where the story shifts from interesting to unsettling. The flare did not just show up in space data, it affected Earth. Researchers found measurable changes in the upper atmosphere. The ionosphere, a charged layer high above the surface, reacted. In simple terms, radiation from a star across the galaxy briefly pushed on the very skin of our planet. Space did not stay out there. It reached all the way here. That is why this event matters so much. Not because it hurt people on the ground. It did not. Earth's atmosphere protected us. But the flare proved something many people never think about. Our world is not sealed off. It lives inside a cosmic environment. Most of the time, that environment is quiet enough for life and technology to ignore. Sometimes it is not. The initial spike of the flare lasted only a tiny fraction of a second, but it carried an absurd amount of energy. Some reports compared it to the sun's output over hundreds of thousands of years, squeezed into less than a second. That comparison is imperfect, like all big space comparisons, but it helps you feel the scale. This was not a bright flash. It was a cosmic detonation. And still, SGR 180620 was not especially close by normal human standards. 30,000 light-years is a staggering distance. The Milky Way itself is about 100,000 light-years across. So this was not next door. Yet even from that range, the flare was strong enough to leave fingerprints and data collected around Earth. That is the detail that keeps pulling scientists back to this event. Nobody expected the atmosphere to become part of the experiment. Yet that is what happened. Instead of only using satellites as detectors, researchers could also study how Earth's upper air responded. It was like the planet itself had become a sensor. For an instant, our atmosphere carried evidence that something catastrophic had happened far away and long ago, and that evidence could be measured. The obvious question follows right away. What if the source had been closer? Scientists are careful here, because they do not like turning real research into movie scenes, but they also do not hide the danger. A giant magnetar flare from much nearer to Earth could do far more than nudge the ionosphere. It could hammer satellites, disrupt communications, and possibly damage the ozone layer if the conditions were bad enough. That possibility is one reason magnetars inspire so much fear and fascination. They are not the most common stellar objects. They are not the brightest things in the sky every night. But when they erupt, they can behave like trapped violence finally finding a way out. And because they are compact, distant, and easy to overlook, they remind us that cosmic danger does not always look dramatic until the moment it acts. To understand why the flare was so intense, you have to understand the body that produced it. A magnetar is not a normal star-burning fuel, it is a corpse. It is the crushed core left behind after supernova. What remains is incredibly dense. A spoonful of neutron star matter, if you could somehow carry it, would weigh more than any mountain you have ever seen. Yet density alone is not the full story. Magnetars also spin, though usually slower than young pulsars, and their fields can become twisted like stressed cables. When the stress grows too large, the crust can fracture in what scientists sometimes call a starquake. That fracture can trigger a violent rearrangement of the magnetic field. The rearrangement releases energy in a sudden burst. The result is a flare that can outshine almost anything nearby. Here's the eerie part. If you had stood on Earth 30,000 years ago, nothing would have happened for you. The flare had already been born, but its light had not arrived. Whole human lineages lived and died in the meantime. Ice ages advanced and retreated. Mammoths still walked. Then, after all of that, the radiation finally reached our planet in a modern century full of satellites and radio systems. That time delay changes the emotional weight of the event. We like to think danger comes from the future, from things moving toward us right now. But this danger came from the deep past. The cause and the effect were split by a time gap too large for normal intuition. By the time Earth noticed, the flare was history. We were reacting to an ancient event, not a fresh one. That also means the star you would point to in the sky today is not the star that existed when the flare began its trip. SGR 1806-20 has kept aging ever since. Its magnetic field has kept evolving. Its rotation has kept changing. When astronomers study it now, they are always working with delayed information. The universe never gives live coverage. It gives archives made of light. For decades, astronomers had seen smaller magnetar bursts and knew these objects were unstable. But giant flares remained rare enough to feel almost mythical. Only a handful have been confirmed with confidence. That scarcity matters. It means we still do not fully understand how often they happen, what exact chain of events triggers them, or how much energy their most extreme versions can truly release. And that uncertainty leads to one of the biggest problems in high-energy astronomy. Seen from far enough away, a giant flare can look like something else. It can masquerade as a short gamma-ray burst, the kind of event often linked to merging neutron stars. NASA and other teams have stressed this point. Without the faint tail and certain timing clues, a magnetar flare in another galaxy can hide in plain sight. That is why the 2004 event became more than a single dramatic story. It became a template. By studying its rise, its decay, and the way its signal behaved, astronomers gained a better pattern for recognizing similar flares far beyond the Milky Way. Years later, when missions saw strange bursts in nearby galaxies, scientists could compare them to the 2004 giant flare and ask whether they were looking at the same kind of monster. In 2021, NASA highlighted evidence that at least some short gamma-ray bursts from nearby galaxies were probably giant magnetar flares. That was a major shift in the story. It meant the event that rattled our own atmosphere was not some cosmic freak that happened once and then disappeared. It was a clue. It was teaching scientists how to identify a whole class of explosions they had been misreading. Suddenly, the 2004 flare looked less like an isolated shock and more like a missing page in a much larger manual. If giant flares can hide among other fast cosmic blasts, then magnetars may be shaping the high-energy sky more often than we thought. The universe may be throwing these tantrums again and again, while our instruments keep filing some of them under the wrong name. That is one reason researchers still revisit old data. Every new insight makes the archive more valuable. A burst recorded years ago can become more interesting after a later discovery changes the pattern. This is a strange feature of astronomy. Sometimes the telescope has already seen the truth. Scientists just need a better question before they can recognize what was captured. And giant flares are not only bright, they are structured. Many show a rapid, brutal spike followed by a tail that flickers as the magnetar rotates. That flicker matters because it helps separate a magnetar flare from other types of gamma-ray events. In the 2004 case, instruments were partly overwhelmed, yet the signal still offered enough clues to transform the event into a benchmark. Then the atmosphere blinked. Before 2004, magnetars were already exotic. After 2004, they felt personal. They were no longer just distant oddities for specialists. One of them had directly altered Earth's upper atmosphere from across the galaxy. That fact pulled magnetars out of the category of abstract astrophysics and pushed them into a new category, cosmic events with measurable local consequences, even when the source seems unimaginably far away. So what exactly hit us? Not debris, not a shockwave of particles ripping through the air like in science fiction. What reached Earth first was a blast of high-energy radiation, mainly gamma rays and X-rays. These forms of light carry far more energy than visible light. You cannot see them with your eyes, but their interaction with matter is powerful enough to trigger chemical and electrical changes in the atmosphere. Gamma rays are the most energetic light we know. They are produced in nuclear reactions, particle collisions, and the wildest astrophysical environments. A giant magnetar flare throws out gamma rays in a sudden spray of violence. When those photons smash into Earth's upper atmosphere, they can ionize atoms, meaning they strip electrons away. That changes how the ionosphere behaves and how radio waves move through it. The ionosphere is a strange layer because it is not solid or visible in the everyday sense, yet modern civilization depends on it. It affects radio communication, navigation signals, and the way charged particles interact with the planet. So when a distant flare tweaks it, even briefly, scientists pay attention. It means the event crossed the line between astronomy and space weather, even though the source was not the sun. Space weather usually makes people think of solar flares and coronal mass ejections. Those are the usual suspects, and for good reason. The sun is close and active, but the 2004 Magnetar flare was a reminder that extreme radiation can also come from much farther away. It was not just another chapter in solar science. It was a warning that the galaxy itself can occasionally intrude on Earth's environment. A lot of people hear that and imagine instant apocalypse. That is not what happened. The atmosphere absorbed the worst of the radiation. Life on the ground was safe. But the event still matters because it helps scientists test where the line is. How much radiation can Earth's protective layers handle? How sensitive are satellites? How would systems react if a flare arrived from nearby? Those are not silly questions anymore. Consider the geometry of the situation. The flare did not need to be aimed like a laser in the human sense. It simply needed Earth to sit within the outgoing radiation. That is another unsettling part of space. Intent does not matter. A dead star does not choose targets. But if your planet happens to be inside the path of a giant flare, physics does not care that life evolved under calmer assumptions. Astronomers think giant flares may begin when magnetic stress builds inside and above the magnetar. The crust, which is solid but under outrageous pressure, can crack. The field can then snap into a lower energy shape, releasing energy almost instantly. If that sounds like an earthquake mixed with an electrical disaster, that is not a bad mental image. Except this earthquake happens on a star made mostly of neutrons. The phrase starquake is dramatic, but it is not just poetry. It points to a real physical idea. A magnetar's crust may behave like an ultra-hard shell under impossible stress. When it fails, the movement can jolt the magnetic field. That jolt can trigger the burst. In some flare data, scientists have even looked for oscillations that might carry hints of the crust ringing after the break. A star had broken and Earth was reading the fracture. There is also a deeper reason the event grabs the imagination. Magnetars are proof that death in space is not quiet. A massive star can end in a supernova and still remain dangerous long after the fireworks fade. The remnant keeps twisting, cooling, and storing tension. Then, suddenly, it lashes out again, not as a living sun, as a compact ruin with a magnetic field too intense to behave politely. That gives the whole event a haunting shape. A star dies. Its core collapses. A magnetar forms. Thousands of years pass. Stress builds. A flare erupts. 30,000 years of travel pass. Then, in one small instant over Earth, detectors spike, data saturate, and scientists realize their planet just got brushed by the echo of a long-finished catastrophe. Few space stories combine time and violence quite like that, and yet the flare did more than scare astronomers. It opened new science. Because Earth's atmosphere responded, researchers could examine the event from multiple angles. Satellite instruments, radio effects, and atmospheric measurements all became pieces of the same puzzle. The burst had effectively turned the space around Earth into a laboratory. Nature had run an experiment no one could have planned, and scientists were left trying to read the results before they vanished. One detail often gets lost in retellings. The flare did not last long, but short does not mean small. In astronomy, some of the most important events happen fast. A second can carry more energy than ages of ordinary starlight. That is why speed itself becomes part of the fear. There may be no long warning, no slow buildup for human observers, just a violent pulse arriving at light speed after a journey of tens of thousands of years. Now step back and ask the question that always arrives next. How rare is this really? The honest answer is that giant magnetar flares are rare enough to be hard to count, yet not so rare that we can dismiss them as fantasy. A few confirmed events are enough to prove the phenomenon is real. A few newly identified candidates in other galaxies suggest we may be underestimating how often it happens. That matters for a simple reason. Risk is not just about power. It is about rate. A truly catastrophic event that happens once in a trillion years is interesting but not urgent. An event that happens every so often in a galaxy full of stars becomes a different kind of problem. You begin asking where the nearest magnetars are, how active they are, and whether Earth lives in a relatively safe neighborhood or just a lucky one. The good news is that SGR 180620 is far away. The better news is that no known magnetar is sitting next door in a way that suggests immediate disaster. Scientists do not present magnetars as an emergency for daily life, but they do study them as a real hazard in the broad cosmic sense, the same way we study asteroid impacts, supernova, and solar storms. Rare does not mean irrelevant. There is another layer to this. Modern civilization is far more exposed than prehistoric life was. 30,000 years ago, a modest atmospheric disturbance from a distant flare would have passed unnoticed by humans on the ground. Today, the same kind of event arrives in a world of satellites, power systems, aviation routes, and fragile global timing networks. Technology gives us reach, but it also gives the universe more surfaces to hit. That is why the Magnetar story feels more urgent now than it would have a century ago. The event from 2004 did not break civilization, but it happened during an era able to measure its effects. If an even stronger event or a closer source ever struck, our dependency on electronics would turn a space physics problem into a human systems problem very quickly. Space is not becoming more dangerous. We are becoming more connected to things space can disturb. Most people still think of Earth as isolated because everyday life trains you to believe danger comes from weather, politics, disease, or geology. Those are real threats. But the Magnetar flare reminds you that your planet is also floating inside a much larger system. The night sky is not a painted ceiling. It is an active place full of remnants, fields, radiation, shock fronts, and old explosions still moving. Nobody expected what happened next. As scientists dug deeper into giant flares, Magnetar started connecting to other hot topics in astronomy. Some researchers asked whether certain mysterious fast bursts from nearby galaxies could be these same flare events. Others looked at how magnetic reconnection, the rapid reshaping of field lines, might power the outbursts. The 2004 event kept returning as a reference point because it was so strong and so local, at least by cosmic standards. It also forced astronomers to face a frustrating truth about their instruments. The very brightness of a nearby giant flare can ruin clean measurement. Detectors saturate. Fine detail gets washed out. That means a closer event can be harder to study in some ways than a slightly weaker event much farther away. The universe is funny like that. It can hand you the most important clue in the room and still make it hard to read. So researchers became interested in extragalactic Magnetar flares, bursts far enough away not to blind every instrument, but near enough to still show their nature. In 2020, one such burst from the galaxy NGC 253 helped strengthen the case that Magnetar giant flares can masquerade as short gamma-ray bursts. That discovery did not replace the 2004 event. It completed it. The old flare became the key that made the new one legible. This feedback loop is one of the best parts of real science. A terrifying event happens. It is partly understood. Years later, a cleaner version appears far away. That newer signal teaches scientists how to reinterpret the older one. Then, the older one, richer in local impact, helps anchor the theory. Step by step, confusion becomes pattern. What first looked like cosmic chaos starts revealing rules, and those rules change how we read the sky. Magnetars may even matter beyond radiation hazards. Recent research has suggested that giant flares could help create heavy elements under the right conditions. That idea is still being worked through, but it shows how these objects keep expanding their reach across astrophysics. They are not just danger beacons. They are laboratories for extreme matter, extreme fields, and processes that may shape how the universe builds some of its rarest ingredients. Think about how strange that is. The same kind of object that can jolt Earth's atmosphere from 30,000 light years away may also help explain how nature forges valuable heavy elements. Violence and creation live side by side in space. The universe does not separate them the way human stories do. It uses the same brutal mechanisms to threaten, build, erase, and reveal. Another reason magnetars matter is that they push physics into places we cannot reproduce on Earth. Their magnetic fields are so intense that even the vacuum around them behaves differently. Light, particles, and matter all operate in rules that become extreme. When astronomers watch a magnetar flare, they are not just logging an explosion. They are watching physics under pressure far beyond any laboratory humans can build. That means every flare is a gift and a warning at the same time. A gift because it lets scientists test theories about matter, magnetism, and radiation. A warning because the same event reminding us how nature works is also reminding us how little control we have over when and where such things happen. We learn from the punch only because the punch lands somewhere we can observe. The 2004 flare also sits at the edge of public imagination because it sounds almost made up. A star the size of a city explodes without exploding. Its crust may crack. Its magnetic field twists. A burst leaves before human history is recorded. Then the message arrives in the age of satellites and changes our atmosphere. If you wrote that into fiction, some people would call it too neat. Reality did it anyway. The sky looked empty. It was not. For most of human history, the sky looked calm because human biology is tuned to visible light and local scales. Gamma rays do not announce themselves in a way our ancestors could notice. But the universe was always active. Magnetars flared. Supernovae exploded. Black holes fed. We were simply blind to most of it. Technology did not create the danger. It revealed the true level of motion overhead. That revelation cuts two ways. On one hand, knowledge makes space less magical and more measurable. On the other hand, measurement often makes space feel wilder, not safer. Every new detector extends the list of things that can touch Earth from afar. Solar storms, cosmic rays, passing dust, near-Earth asteroids, magnetar flares. You're not becoming paranoid when you notice this. You're finally seeing the environment your planet has always occupied. There's a phrase astronomers often use without drama: upper atmosphere effects. It sounds mild, clinical, safe, but unpack it and the meaning gets heavier. A dead star across the galaxy changed the state of Earth's high atmosphere. That is what the phrase means. The planet responded physically to a signal from ancient deep space. The wording stays calm because science is calm. The reality is still astonishing. Once you accept that, the bigger question becomes impossible to ignore. What are the true limits? How close would a magnetar flare need to be before Earth's natural shielding was no longer enough to make the event just an atmospheric story? Researchers model these possibilities carefully because the answer depends on energy, distance, direction, and timing. But the broad conclusion is clear: closer would be much worse. A flare from a nearby magnetar could strip away ozone or at least damage it significantly, depending on the event. That would not mean instant doom, but it could let more harmful ultraviolet light reach the surface, with consequences for life and ecosystems. Satellites would likely suffer first. Communications could fail. Navigation systems could glitch. In the modern world, even a short disruption at the wrong scale can ripple into transportation, finance, defense, and emergency response. This is why people sometimes compare giant magnetar flares to a kind of cosmic sniper shot. The image is imperfect because the star has no aim, but it captures the suddenness and the long reach. A single compact source, far away, unleashes a burst that crosses enormous distance and still matters when it gets here. The universe is mostly empty, yet emptiness does not prevent concentrated violence from traveling cleanly. And there is a darker philosophical edge to the story. The flare that touched Earth in 2004 began its journey before anything like modern human memory existed. That means some dangers do not care about our timelines at all. Civilizations rise in the middle of ancient processes already in motion. We like to think history starts with us. The cosmos keeps proving that it does not. That may be the deepest reason the event feels unsettling. It collapses the distance between cosmic history and human fragility. One side of the story involves neutron matter, magnetic collapse, and relativistic radiation. The other side involves your atmosphere, your satellites, your communications, your sense of safety. Those two scales should not feel linked. Yet for a fraction of a second in 2004, they were. Here's the climax of the whole story. The burst lasted less than a heartbeat, but for that instant, the flare from SGR 1806-20 was one of the brightest extrasolar signals ever measured at Earth. Not brightest star, not brightest object in the sky, brightest incoming burst from beyond the solar system. A dead star, no wider than a city briefly outshone almost every distant thing our detectors could compare it to. Small object, terrible power. Scientists believe the flare's initial spike was followed by a tail modulated by the magnetar's spin. That tail mattered because it helped identify the source class. Each rotation changed our view of the emitting region, like a lighthouse turning. Even in chaos, there was rhythm. Even in a blast powerful enough to blind detectors, there were fingerprints subtle enough to teach us what had happened. And while the flare itself was ancient by the time we saw it, the information inside it was fresh to us. That is another beautiful cruelty of astronomy. The event is over before Earth is born into the knowledge of it, yet the knowledge can still be new, sharp, and urgent on arrival. The universe sends no warning labels. It only delivers light, and you must learn to read the light after it hits. There's a reason some astronomers never stop thinking about December 27, 2004. It was not merely a strong detection, it was a scale correction. It forced scientists to update their instincts about what magnetars can do and how a flare from inside our own galaxy might interact with Earth. After that day, any discussion of magnetar hazard, giant flares, or high-energy templates had to take the event seriously. It also changed how people think about short gamma-ray bursts. If some brief high-energy bursts in nearby galaxies are really magnetar flares, then the high-energy sky has been partly misfiled. That means rates, populations, and energy budgets may need revision. In other words, the flare did not just scare us, it rearranged catalogs. It forced a classification problem, and classification problems often hide the biggest scientific revolutions. Because the moment you realize one kind of event has been wearing another kind of mask, every old record becomes unstable. How many bursts did we wrongly label? How many giant flares are buried in archives? How many theories about short bursts need to be adjusted? The 2004 event kept growing in importance because it was no longer just a memorable blast. It was the Rosetta Stone for a whole confusion in astrophysics. The story becomes even more dramatic when you remember how narrow the safe outcome really was. Earth was far enough away, and the atmosphere thick enough, that the result was limited mostly to upper atmospheric effects and instrument shock. Move the same event closer, and the balance changes. Nature did not choose to spare us out of kindness. Distance spared us. That is a colder, more honest comfort. And distance is not a shield you control. You do not negotiate with it. You simply happen to live where you live in the galaxy. That randomness humbles people. Our planet feels central in daily life, but cosmically, it is a moving target in a wide disk full of stars, remnants, gas, radiation, and ancient violence. Safety is often just geography plus time plus luck. That is the real payoff promised at the start. A Magnetar did not literally aim at Earth with intent, but its flare did sweep across our planet after traveling for about 30,000 years. It changed our atmosphere enough to be measured. It taught scientists how to find similar explosions in other galaxies. And it proved that one of the most intense messages Earth can receive may arrive from the deep past without any chance of warning. The flare ended. The consequences did not. Then comes the thought nobody likes to hold for long. Somewhere else in the Milky Way, another unstable magnetar may already have cracked. Another giant flare may already be on the way, not because it is happening now, but because it happened long ago and its light has not reached us yet. That idea is perfectly consistent with physics. It is also almost impossible to live with emotionally, so most people never think about it. But scientists do think about it, at least in the abstract. That is what good science requires. You do not stare only at what already hit. You map the population, study the mechanisms, refine the rates, and learn what early clues might matter. You accept that prediction will never be perfect. Still, better understanding turns dread into preparedness, and preparedness is one of the few real advantages intelligence gives a fragile species. There is some comfort in that. The same technology that made civilization vulnerable also made awareness possible. Satellites that can be disturbed by radiation can also detect that radiation. Global networks that depend on stable signals can also share warning data fast. Humanity may never control magnetars, but it can become less blind. Sometimes survival begins not with power, but with earlier knowledge of what kind of universe you actually inhabit. Even so, no model removes the awe. A magnetar flare is not only a hazard, it is a vision of matter and field pushed to extremes that border on the unimaginable. It tells you what happens when stellar death does not settle quietly, when the leftover core becomes a locked box of pressure and magnetism, and when that box opens for less than a second with more force than the sun spends over ages. Few natural events compress so much meaning into so little time. In one flash, you get stellar evolution, nuclear matter, magnetic instability, gamma-ray astronomy, atmospheric chemistry, classification puzzles, and existential risk. That is why these stories spread beyond science journals. They satisfy something ancient in the human mind. We want to know what hunts in the dark, even when the answer is not a creature but a physical process. And yet the physical process can feel more frightening than any monster. Monsters live in stories. Magnetars live in the same galaxy as Earth. Their rules are not symbolic, they are numerical. Distance, energy, angle, shielding, ionization. These are cold words, but they govern real consequences. When a giant flare arrives, there is no negotiation, no hero, no speech. There is only whether your planet is prepared enough and far enough away. That is why the 2004 event still echoes through public imagination. It condensed a cosmic lesson into one unforgettable fact. A star corpse across the Milky Way changed something measurable on Earth. You do not need equations to feel the power of that statement. You just need to understand that the sky is not passive scenery. It is an active system, and your world sits inside it whether you think about it or not.